In this video, we will discuss calling tools with Arcpy. Here are some of the subtopics we will be discussing. We'll start with Python capabilities in ArcGIS. Arcpy is the name of the ArcGIS Python Application Programming Interface, usually abbreviated API. You may have heard the term API in some other contexts. Perhaps you've heard of the Google API, which is a JavaScript language API that allows you to customize your Google Maps with code. Similarly, Arcpy is a Python API for ArcGIS applications. To use it, you import Arcpy. You've seen this in a couple of example scripts already. Note that Arcpy is not a standard Python module like sys and os are. So it's not installed necessarily when Python is installed, but it's installed when ArcGIS is installed. So if you get on a machine that doesn't have ArcGIS, you won't be able to import Arcpy. This is a list of some of the main topics that we'll be discussing and the main functionalities that are there, kind of an outline. You can see some examples over here. You can call tools, check out extensions, set overwrite output to be true, meaning output can be overwritten, describe data. If you have data coming in from user input, you may not know whether it's a raster or a geodatabase and so forth. If you have a workspace setup which has multiple files of a certain kind in it, you can list all of those files, get a list automatically in your Python, and then do Python operations, perhaps call tools on those files. So for example, you can list all of the feature classes within your workspace. There are also cursors which allow you to read and modify the attribute tables of ArcGIS recognizable files or readable files. If you have a search cursor, you can read through it, but you can't modify it. But there are other cursors that allow you to modify the table. Getting and printing geoprocessing messages can be done with Arcpy, and you can also manipulate map layers and modify the symbology to some extent with Arcpy. Highlighted are the topics that we're going to discuss shortly. The table you see here is a mnemonic to remember the parts that are there in Arcpy. It doesn't have all of the details, but it gives you a summary of the functionalities. As we work through the Arcpy material, we'll be stepping through this. This is available in Chapter 5 Data Directory, location listed at the bottom of the slide. Each part of this diagram has related functionality. The boxes are meant to divide it up in that way. The left box has Arcpy functions that you call Arcpy dot and then the function name. The green box has describe functionality. Mentioned earlier, you're able to get the program to tell you what kinds of properties the data has. Enumeration, we had the example of listing feature classes on the previous slide. And cursors, there are some other objects that we'll discuss. And the mapping module. Finally, you have the key for the cheat sheet down here. The items that have a plus next to them, a single plus, are read-only. Those with double plus are read and write. In other words, you can see them and modify them. And those with an arrow are methods, which is another word for functions that are associated with a certain type of object. And classes and packages or modules, we'll discuss those terms later. This little box down here is a reminder that the environment settings can be set with Arcpy. For any of the things that are on this table, you can use them once you have imported Arcpy. And the way this table was highlighted pretty much the order in which we will be discussing the items that are in there. This is the historical look at how it used to be. Now it's import Arcpy. It used to be import ArcGIS scripting. The only reason I bring this up is because you may find old code that you want to use, and then you can recognize that it was written for 9.2 or so forth, and try to update it. The script will run this. You can still import ArcGIS scripting, but you may be using other things in your code, so to put it together you might need to modify it. You used to have to create a GP object, and then you would do things to the GP object instead of importing the package, Arcpy package. Everything in Python is an object, and we will get more into the concept of object-oriented programming later, but we'll just say for now that OOP code revolves around objects instead of being functions put together. So you have to think about the objects in your program that you want to develop, and then they have methods and properties associated with them. Later we'll get into defining your own classes, and that's how you can create your own kinds of objects. Objects, for now we'll just say, okay, we know that object-oriented programming is the basis for Python, and we're going to see a lot of these terms for when we're dealing with Arcpy and other built-in data types as well. We saw that the integer objects, you can just create one of those. So when you say x equals 5, you're creating an instance of that data type. So x is then an integer object. And objects can have methods and properties. A method is a set of code that's a function that's associated with an object. So it's a set of code that performs some action related to its object. For example, replace and lower are examples of string methods. And objects can also have properties. A property is a variable associated with an object. As an example, arcpy.env has a workspace property that you can set. The workspace property happens to control where it will look for input data if you don't specify a full file path, and where it will place output data if you don't specify an output file path. Another example is the overwrite output property. When you set that to true, it allows the Python to overwrite existing files without throwing an error. Just to review object-oriented programming terminology, let's go back to some things that you already know. So take a moment to write some Python code to create objects as described here. Just pen and paper will do. Number 1, create a float object named x with a value of 5. Notice that's a float, not an integer. Number 2, create a string object named filename and give it a value of park.shp. Number 3, create a list object named mylist that contains the integer objects 1, 2, and 3. Pause your video right now if you're not ready to see the answers. For the first one, x equals 5.0 will create x as a float object. You may have thought about, say, using casting. X equals float parentheses 5 in parentheses. But you don't need to do that. A simpler way to do it is just use a decimal in the number, and then Python will automatically dynamically type X as a float when it detects the dot in the number. To create the string object, you use an assignment statement with a string literal on the right. To create a list object, remember to use the square braces, comma separated items inside. We can set environment settings with Arcpy. You're probably familiar with how to set environment settings by hand by using ArcGIS geoprocessing menu, environments, and then you can go in and set them within the graphical user interface. Any of these environment settings that are settable here can also be set with Python. Here we're using a Arcpy list environments method to get a Python list of each of the environment settings that are available to be set within Python. Remember what the U stands for and what that means? These are Unicode strings. For all practical purposes, you can just ignore the U. Using Python for environment settings, you need to use env, which is a submodule that handles the environment settings, and double dot notation. There's a dot after Arcpy and a dot after env, and then the property. For example, arcpy.env.cellSize, when we enter that in the interactive window, it prints max of. This is the default value for the cell size. If you alter that, then it will print whatever you alter it to. Max of will use the maximum cell size if you're processing a number of rasters at the same time. Whichever raster has the largest cell size, that's what it will use. The no data property is another example. The default value is all caps none, the string. This is different from our built-in constant, which is a Python object. This is just a string with the letters N-O-N-E inside of it. But that's the default value of no data. These are examples of getting the values of the existing values of the environment settings, and down here we have two examples of setting the values of some environment settings. Setting override output to true, setting the workspace to this database. So you use assignment statements to set those. Python can call any of the tools in ArcGIS Toolbox, with one exception, that's raster calculator, and we'll speak specifically to that in a few minutes. Arguments are specified in parentheses, and those give the tool input, just like when you input them in the GUI when you're running it by hand. The format is object.method underscore something, which I'll let you guess at for a moment, parentheses, and then a list of arguments, comma separated. In this case, there's only one argument. Are you familiar with the compact tool? This tool will take a database as input and clear out any memory that doesn't need to be used, so it'll kind of clean it up. If you have, for example, deleted some files from a personal geodatabase, some records from a personal geodatabase or a table that is no longer there or is half there, you may notice that your personal geodatabase size remains the same. So somehow it's not pointing to that information anymore, but it's storing it somewhere. This compact tool will reduce the size of the file appropriately. Now, are you ready for the reveal? What is the underscore management in this example? And by the way, the object.method should look familiar. It's just like how we did the lists and strings and sets and tuples. Ready for this one? That specifies the toolbox. The compact tool is in the data management toolbox. There are aliases for each of the toolboxes. A number of them are listed here. So in other words, you don't have to write out data management tools, you just write the word management. Analysis tools, write the word analysis, and so forth. The reason that you have to specify the toolbox is because some tools may be named the same thing and be in different toolboxes. This is an example. Which toolbox is the buffer analysis tool in? Oh, it's in the analysis toolbox, right? We just got done saying that that's the alias back here. And this one is in the coverage toolbox. How about this one? We don't know. This would throw an error because Python won't know either. Arcpy won't know which tool to call. A summary of what we've just discussed: to assign a value to a property, use object.property equals the value that you want to assign. To get a value of a property, say you want to print it out or use it somewhere else, just say object.property. To use a method, Arcpy method, you say object.method. And here are 3 examples. You can call the buffer analysis tool. You can also call exists, and this will return true or false to see whether that file exists. This can be really useful sometimes when your code isn't working and you want to make sure that according to Arcpy, the file that you can see in your directory or in your workspace is there. If it says false, then you know maybe something's wrong with how you've specified the workspace or perhaps how the name is spelled. You can also check out extensions for advanced tools like network analysis, and there are aliases for that. So these are 3 examples of object.method where the object is Arcpy. And there are parentheses around, they're all followed by parentheses with comma separated arguments when there's more than one argument. The workspace property specifies a default location for tool input and output. So if we set the workspace to cdata.gdb and we call the buffer analysis tool in this way, it will look for pond in this workspace and try to output buff to this workspace. So it has the same effect as writing these full paths. Usually it's good practice to set the workspace and then not write the full paths if it's going there, because as your code grows and you are calling multiple tools within the code, it becomes a lot to try to maintain those paths throughout the code. It's always better if you're using one string literal many places, to use a variable to hold that, so that when it comes time to update it, you just have to update it and make sure it's correct in one location in the code. It also makes your code a lot cleaner and easier to follow. If you're going to call this line of code, you have to have set the workspace environment before you call this, because it will otherwise not know where to find the data. If you use this line of code, you use the full path file names, full path meaning starting from the hard drive specification up to the end of the file name, then you don't need to set the workspace. For shapefiles, the .shp extension is required for the input names. If you try to say this is your shapefile and you have set your workspace to ctemp, even if you have cover63p.shp in your ctemp directory, it will throw an error. Input features dataset does not exist, so you need to use that shp on the end. However, you can get away without specifying the extension for the output. The output will then be a shapefile if it's in a folder or a directory, but if it's in a file geodatabase where feature classes don't have extensions, it won't have the extension. Oftentimes, we'll want to get our input from one place and place our output in a different location. The way that the tool calls are set up, if you use only the file name for the output, this is the input file, the output file name, and the buffer distance. If you were to say just BUFF here, it will by default put it into whatever the current workspace is. In this case, we've specified. If you want to, say, have it write the data out to an output directory, then you need to specify the output file path as something other than the workspace. So you can use the full path file name. You can use a variable to store that information, or you can use a relative path. This is a relative path. Say we have c/datadir, and there's another directory underneath of that called out, O-U-T. Then this would be a relative path from our current workspace to the out directory, and followed by the file name. So again, that's absolute path that's going from the hard drive to the end. That's the full path file name. And a relative path can say my current position and move from there. It implies that the current position is the starting point. You may have noticed if you try to run a tool twice, a call to a tool twice in Python, with the same output name, it'll give you an error. So for example, if we call the buffer tool with lakes as the input and buff as the output, we get that created. If we then call the buffer tool again with ponds as the input and buff again as the output file name, it will give an error that says output feature class, meaning that's where there's a problem. Dataset ctemp buff already exists. Failed to execute buffer. If you are working with sample scripts or working on homework, usually you'll just want it to overwrite that existing file. So we'll often put this statement inside of our homework scripts, where it sets the overwrite output environment setting to true, and then you won't get that error when you try to run it again. It'll just create it and silently overwrite the old file. Just like this. One caveat, however, when you're working with this override output, sometimes you may see behavior that doesn't make sense based on what I just said. If you have oh, sorry, that's not the problem I wanted to talk about on this bullet. If you have a value of true for the current session, then you will have the value of true for in the entire current session unless you set it back. So say you do homework script number 1 and you set override output to true in that script, but then you do homework number 2 and you set override output. You don't set override output at all in that script, but you run it within the same session, then you'll find that it will still overwrite the output, but you haven't, if you close that current session and open it again, that second script won't overwrite the output. So I think I mentioned this earlier, it's a good idea to restart Python Win and test code before sharing it with others. ArcGIS Resources Help page changes every year, but there's always a search window. And so you can search on the tool that you're trying to run, and you will get a help page which will be fairly consistently the same. It always has a syntax section and a code sample for the Python. When you search on something generic like buffer, you may get a lot of hits, but you'll notice that the output from the search will usually have the toolbox behind in parentheses, so that can help to boil down what you're getting at. So we'll talk about these syntax section here. The syntax has a table that is listing every parameter that the tool can take. This table is given from top to bottom in the same order as the GUI choices. The graphical user interface, when you run the tool by hand, gives you boxes to fill in. And these correspond directly with what you see in the graphical user interface. The input features, in the table it says in_features, output feature class, out feature class, linear unit, buffer, distance, or field. That corresponds to the distance, value, or field, which can be linear unit or a field that you specify for the buffer. And then we have four more optional parameters that can be specified. Let's take a closer look at this table in the next slide. Just above the table, you'll see syntax and then what we call the blueprint or the signature for the function. This is a template which doesn't say, it's not exactly code right here, it's an example of what parameters can be passed into the tool, and it's just listing these names that you see in this column. Some of them have curly braces around them. Those are showing the optional parameters. If they have curly braces, then they're optional parameters, which can just be left out when you call the tool. You may have noticed we've called this tool several times, and sometimes we only use 3 parameters. The parameter explanations give you some idea of what they're expecting in each of these positions. The data type here is it's the ASRI data type that we're talking about. In fact, when you call this buffer tool, you use a string data type to specify the feature layer that you want to work on. You use a string to specify the feature class name, and you use a string to specify the linear unit that you want to, or the field that you want to use for the control the buffering distance. To use some but not all of the optional features, so if you don't want to use any of the optional features, you can put in this example 3 parameters and end the parentheses. If you want to use the first optional parameter, you can just put that behind there. If you want to use them in order, you just put them in the order that they appear. But if you don't want to use one of them, but you want to specify another one after that, you have to use a placeholder because it doesn't otherwise know which parameter you're specifying. So we say input, output, buffer distance. This is the line side, which is the side of the line to be buffered. We are not specifying this. That means it will take the default, which is full. But we want to specify the line end type as flat. We don't want to take the default for that. So that is why we had to put a placeholder so that we could put this in. Otherwise, if we just put flat after 1 mile, it would try to set the line side as flat, which it wouldn't understand. So notice when you go take a look at the help, go ahead and go over there and search on your favorite tool, and you'll see the template for the Python code when you roll down to the syntax section, just above the parameter table. The table has a parameter, name, an explanation, and an ESRI data type. The table will have the required parameters listed first. They're always all the parameters are listed in the order that they need to be placed in, as the template shows you, into the parentheses. And then they will specify optional. In a few cases I've noticed that the table does not have optional in parentheses, but the curly braces in the template will tell you that they are optional. Here's a tip. You can run a tool with the graphical user interface, with the regular dialog box, and copy a code snippet. It creates a code snippet which you can find in the results window under the geoprocessing menu. You can copy that by following these steps listed here. That way you can start your Python code calling that tool, not from scratch, but with an example with the code filled in. One caveat, though, to using code snippets is that they generate code that will look slightly different from what you're used to seeing in class. They generate code that uses something called keyword arguments. So far, we've been working with positional arguments. Positional arguments are ones which must be provided in the order specified in the function signature. Unlike positional arguments, the ordering of keyword arguments doesn't matter. Instead of order, assignment statements are used to specify which options are being set. The option name goes on the left of the equal sign and the value on the right. You can see this in the code snippet example shown here. This was created by running the tool on the farmland shapefile with a 200-yard buffer. The first keyword argument here is inf_features with a value of C GIS540 scratch farmland. Then we see a comma, and then on the next line, out_feature class and its value. Each argument is separated, still separated by a comma, but in this case, there's an assignment statement for each argument. Okay, and when the code comes directly from the code snippet and is pasted, you paste it into your window, it won't look nice and tidy like this. I actually hit return after each of the commas so that you could read the assignment statements more clearly, and I would recommend that you do that yourself so you can see more clearly what's going on in the code. So a positional argument is equivalent. You see that I've got it given an example that's equivalent in the next block of code. So either keyword or positional arguments can be used in your code. They have the same result. Many programmers actually prefer keyword arguments because the code is more stable when functions are modified, sort of when they change versions, there might be changes. Although I've seen Arcpy be quite stable all the way back from 9.1 up to 10 star, shall we say, and through Pro, the calls to the tools have been pretty consistent. Another advantage of keyword arguments is that the parameters are more explicit. So if you're strange to the code or new to the code, you see, oh, that parameter is specifying the input features, that parameter is specifying the output features without having to look it up in the documentation. The only drawback, of course, is that there's more code required. So it's slightly more crowded, less clean. Another difference with code snippets, you may have noticed that the optional parameters are included when the code snippet's generated. So I ran this tool with all only the default values for the optional parameters, but it spit out the default values regardless. So you can clean up your code that you get from a code snippet by removing those optional arguments when you want to accept their default values. The typical flow for a geoprocessing script is to first import Arcpy and set the environment and output directory, then initialize the additional parameters, and finally, then the tool can be called using the object.method _ toolbox and alias with the arguments passed in there. So let's look a little more closely at this. We import Arcpy and then we set the workspace. We're using data that's in the Chapter 6 directory. We're going to set a variable called output_dir to this string literal, which is the scratch directory under GIS540. And then we're setting the override output environment variable to true so that we can run the script more than once and the data will just be overwritten. Here we create a variable called input raster and set it equal to the raster. This is a Esri grid raster. They don't have file extensions. Rather, they have a folder and subfolders with lots of files in them that make up the grid raster. And when you specify a grid raster, you don't have to, well, there is no file extension to specify because it's simply the name of a folder. Then this code uses concatenation to set the output file path to C GIS540 scratch output.txt. So this line of code is so that the output will go into a different directory from our workspace. If we took out the concatenation and just said output.text, where would the output go? If you said to the workspace, then you are correct. Let's look at this code. Arcpy.raster to ASCII _ conversion input raster output file. The tool is named raster to ASCII. The toolbox is the conversion toolbox, and the first parameter is an input raster. The second parameter is an output file, and there are named variables we're using. And that's it for that one. For many tools, we have to set a distance or aerial parameter. To set those, we use a string. The linear unit can be centimeters, degree, decimals, decimeters, feet, inches, and so forth. These linear units are specified as a string with a number and optionally a unit of measure. The number and the unit of measure have to be separated by a space, for example, 5 space miles. This table shows the linear units that they've listed, but there are a lot of variations on this that will be accepted. For example, both single and plural can be given, and certain abbreviations are accepted. You can always check that by trying something, and then you'll know whether it worked or not. If you only specify a numeric value and the distance unit is not specified, then the tool uses the units of the input feature unless the output coordinate system environment property has been set. Let's look at an example now. Suppose there's a small forest fire and you want to find out the portion of a park which lies within a 1 mile radius of the fire damage. So you have a shapefile that is the fire damage and a shapefile which is the park. These polygons are the park. You want to find a 1 mile buffer around the fire damage and then clip that park data on the 1 mile buffer. Let's write a Python script to do that. If you go to today's class and click on In Class, it'll lead you to the description for this, which asks you to write a buffer_clip.py Python script, which will find a 1 mile buffer around the fire damaged region, and then clip the park region that's within this 1 mile buffer. So you'll find a buffer and then clip using that output from the buffer file. You can refer to the help template that's linked here that has the template or the blueprint for the clip tool. We haven't given an example for that yet. The input data is in the Chapter 6 directory, and write the script so that the output, both for the the buffer and the clip, will be placed in the GIS540 scratch directory. Pause the video now and write the script. When we return, we will discuss the solution. We'll step through now. First, your script should have import Arcpy as the first statement, and then set the workspace to that Chapter 6 directory where your input data is. You can create a variable for the output directory, set override output to be true so that you can run it more than once. Then set up your variables for your data. The fire damage we said was in the special regions shapefile. buffer is what we're going to create, so we'll use concatenation to put that in the Scratch directory. Parks poly is our park shapefile, and then we'll have a clip output that will also be put in the Scratch directory. So we call the buffer analysis tool using fire damage as the input, fire buffer as the output, and 1 mi as the linear unit that specifies the buffer distance. Then we can call the clip tool using, this is also in the analysis toolbox, arcpy.clip_analysis, the input file path, the input file name, the output full file name, the clipping file name, and the output full file name. The clip tool takes 3 required parameters: the input, the file on which to clip, and the output. Notice here that we're using fire buffer as an output here and fire buffer as an input in the next call as a clip feature. It's fairly common when you're doing geoprocessing to need to call multiple tools and use the output from one tool as the input for the next. This is another reason why it's a really good idea to have variables that hold your file names so that you can make sure that the value is consistent, and that if you change it in one place and don't change it in another, you don't get in trouble because you can just change that one variable that holds the file name. Some tools take Python expressions as input. This will be specified in the template simply as expression. For example, the calculate field data management tool takes the third parameter is an expression. We can suppose we want to set the result field in a data set, data1.shp. So we want to set that field value to 5 for every record. We can take the calculate field underscore management and then pass in the data name and field name that we want to modify, followed by the expression. The last parameter is saying that the expression that's been passed in is a Python expression. Another alternative is Python 9.3 or VB, which stands for Visual Basic, and VB is the default. A slightly more interesting example, suppose we have a field named measure and a field named coverage, and we want to calculate the value of our result field as 2 times the measure value minus the coverage. When we specify field names in our expression, we have to put exclamation points on either side of them. So the expression itself is a string in this case. If it's not just a numeric value, then it needs to be a string. So we have a string literal with 2 and then the Python for multiplication, which is the asterisk, measure, bang bang, minus coverage, bang bang. We set that expression variable as a string and then pass it in down here and tell the tool that we're using a Python expression. Feature class field calculation expressions can also use the shape field. The shape field contains a set of Arcpy geometry objects, such as polygons, points, lines. Arcpy geometry objects have properties like area or length. You can use these properties with a dot notation on the shape field in the expressions that you pass into a tool that takes an expression. Here our example calculates a field named poly area for the special regions shapefile, which is polygons. We set our expression on the third line. Bang, bang on either side, and shape, that's because we're specifying the shape field, dot area. So this will populate the poly area field with the area of the polygon in that associated with that record. Some tools take multi-value inputs. You will see in the table for those tools something like this, which has square braces, inputs, comma, dot, 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 square braces. That is specifying that it can take a list or multiple values as that input. Can be one or more values. To call a tool that with multiple values, you can use a Python list or a semicolon delimited string or an Arcpy value table object. These are the three techniques, examples of the three techniques below. The first one is using the list. Input files is a list, and it's going to merge these three input files, park, special regions, and work zones, into a new shapefile named merge data. This does the same thing, but uses a semicolon separated string, semicolon separating each of the names. We also call it semicolon delimited. It's delimiting where one name ends and the other name starts. Just want to show you the value table, which might be, you might need to use it for some other tool as well. This is another Python Arcpy object. If you say arcpy.valueTable, if you call that method, it creates a value table object for you. The value table object has methods such as add row, and this will add a new row each time you call it. It'll add a new row with the name that you've specified in there, or you can add a list of items to create the row. Then we would call the merge management tool with VT as the first parameter. We can pass that in. This video, covering the first part of the calling tools with Python slides, began with a broad overview of Arcpy capabilities. Then we narrowed in on the capability to call tools. But before we did that, we went over dot notation. Dot punctuation goes in between the variable and method, like string dot replace or list dot sort. Now, looking back at calling tools, the same pattern can be seen. Arcpy.clip and so forth. Environment settings like setting the workspace and overriding output also use dots. In these cases, it's double dots. So the main discussion was on how to call tools. A tool call always starts with arcpy dot, then the tool name, then underscore, and then the toolbox alias, followed by parentheses with arguments. The arguments are either required or optional, and when using some but not all optional arguments, a placeholder may be needed. Many Toolbox tools take input and produce output data. Specifying a workspace means that full paths for data don't necessarily need to be used. When calling an unfamiliar tool, you can use the online help to see the tool template or signature, which is a blueprint for how to call the tool. The parameter table below the signature shows which arguments are required and optional, and describes the purpose of each of these parameters. Code snippets can be used in concert with the online help. Just be sure to note the keyword argument format they provide. This video also included an in-class exercise to practice calling tools sequentially. Often the output from one tool is the input to another tool, as we saw with the buffer followed by the clip. And you could just use the same variable in both of these tool calls. A few tools, calculate and calculate field in particular, take Python expressions as input. These require the use of the exclamation marks when specifying field names. The expressions also give access to geometric properties, like the area of a polygon for each record. Still, other tools take multi-valued inputs. Examples include the merge tool, the union tool, and the intersect tool. These can take a list of values as input data to be merged, unioned, or intersected. So in the next video, a few additional topics related to calling tools will be covered. One important area is spatial analysis, which we haven't discussed at all, and that works differently. So the same slide set will be continued in the next video.